Imagine you have an object that's somewhat irregularly shaped. For example, something that looks like this. Maybe it's sort of uniform at the top, but then as we get closer to the bottom, it becomes a little bit wider. So something shaped like that. Let's say we take that object and we mount it around a pivot close to the top, and we allow it to swing. Imagine what's going to happen. That object is going to swing back and forth. It's going to swing back down to equilibrium, up to the left, back down to the right, and it'll have some period and some frequency of oscillation that depends on a number of factors, like how big it is, its mass distribution, its length, all of those things. We want to figure out, how do I predict the period of such an object? So let's make a few definitions and get started. First of all, let's define or approximate the location of the center of mass of this object. Let's say it's somewhere around here. If this were something uniform like a rod or a disc, we'd know the center of mass was exactly at the center. But for something like this, let's just say we know where it is, it's closer to the bottom. Now let's also define the distance between the pivot point and the center of mass as d. Let's say I'm pivoting it around this point P, and I'm going to actually draw a set of axes, a vertical axis here and a horizontal axis, representing that I'm pivoting it around that point. And let's label theta as the deviation off of the vertical of the object. So when it's hanging vertically, theta is 0, and as it swings up to the right, theta increases in the positive direction. As it swings up to the left, theta increases in the negative direction. So theta is our deviation off of equilibrium. A few other terms are going to be important, so let's just define them right at the start. Let's figure out the moment of inertia around that point P. If you remember, the moment of inertia around that point P is that pivot point, is going to be equal to the moment of inertia around the center of mass plus md squared because of the parallel axis theorem. And since we're a distance d away from the center of mass, that's our moment of inertia around this new point. Here's our strategy. We want to know the period of this object. We suspect it's undergoing simple harmonic motion. We're going to write the torque equation, sigma torque equals I alpha, and see if this equation winds up falling into the form of the equations that describe simple harmonic motion. Before we get started, let's move over to the side and actually remind ourselves of the form of the equations for an object undergoing simple harmonic motion. Remember, simple harmonic motion is all about the restoring force being proportional and opposite to the displacement itself. I move to the left, I get pulled to the right. I move to the right, I get pulled back to the left. And the value of that force is proportional to the amount of displacement in a linear way. That's often written like this. K is just a proportionality constant, F is the restoring force, and the negative represents that we're always being pulled opposite the way we're displacing, like in the case of a spring or a pendulum. I'm going to take this a step further. We know F equals ma, so I'm going to write that as m times the second derivative of the position, and that equals negative kx. And then if you remember from last Thursday's class, we said d squared x dt squared, the acceleration, is negative k over mx. And then our final little step was to define the angular frequency of oscillation. D squared x dt squared equals minus omega squared x, where omega was defining the frequency of oscillation of the cosine and sine functions that describe this motion. We went ahead and we said, this is satisfied by equations of the form x of t equals some amplitude times cosine of omega t plus a phase constant phi. Omega is that frequency of oscillation, and if you just double differentiate this and plug it back in, you'll see that it satisfies this equation up here. Omega was equal to 2 pi times the frequency, which meant that frequency, the actual frequency in hertz of the object, was omega divided by 2 pi. And then since period was 1 over frequency, the period was 2 pi over omega. This is a physical thing that we can measure. We can measure the period of oscillation and we can see if it follows the prediction. That's what you're going to do in this activity once we derive the expression for the period of a physical pendulum. So now let's come up here and take a look and say, all right, let's write the torque. To do the torque, we're going to need to do something similar to what your book did about the regular pendulum. We're going to need to actually draw some forces. Let's draw the weight, mg, acting from the center of mass. Notice that the weight is at a moment arm of d from the pivot point. But remember, it's only the perpendicular component of that force that actually provides a torque, so we only need the mg sine theta component. The vertical or the radial component, mg cos theta, does not provide any torque. Coming back up to the torque, we can remind ourselves also that that torque is opposite the displacement. So as the displacement moves to the right, that torque is going to pull to the left. And so that torque is going to be negative mg sine theta times the moment arm, which is d, the distance between the center of mass and the pivot point. And that equals I around the point P times alpha. Now this does not look like an equation for simple harmonic motion, but with a little manipulation we'll see that it does. First of all, we need to come down here and remind ourselves of something else that was in your reading, and I mentioned it briefly in class, that for tiny, tiny angles, sine of theta is about equal to theta. This is actually true of thetas and radians, and you just take a super small theta like 0.01 or 0.001 and you plug it in radians to sine of theta and take the sine of it, you'll get the same number back. This comes from something in math called the Taylor series expansion, which I know some of you have learned and some of you have not learned, but there is a formal way to show this, but informally, just try out tiny values and see that it holds true as long as theta is small. So we're going to use this relationship. We're going to use the fact that sine theta is about equal to theta, which means we're confining ourselves to only smallish oscillations of this pendulum. If the oscillations get too big, our data is going to break down. All right, so let's come back up here. I'm going to erase this because it's in my way, but you remember that was just the component of the weight that provided a torque. So I'm going to do this as mg d, and instead of sine theta, I'm going to replace it with theta for small oscillations, and that equals I times alpha, but remember alpha is the second derivative of theta. One more step is minus mgd over I. Remember I is around the point P, the pivot. That equals doesn't equal I because I already divided by it. That equals d squared theta dt squared. Now if we compare our equations, we see we have a second derivative, just like we have a second derivative here. We see that we have, oops, I actually forgot my theta. Let me put it back in. mg dy times theta, I forgot that. We have x, just like we have theta. And then we have the negative omega squared term, which is going to be this. What this tells us is that theta behaves like the variable x does. For like a spring being displaced to distance x, when you displace a pendulum at angle theta, it's going to oscillate, and theta obeys the equations of simple harmonic motion. So we get that mgd over I to the square root is equal to omega. And then using this relationship down here, we can say that period, which is 2 pi over omega, equals 2 pi times the square root of I over mgd. This is the result that you are going to use in your little activity. For the object that you have at home, which will be a disc or maybe a rod, if you want to use a rod, you can calculate the I around a displaced pivot point using the parallel axis theorem. That will be mass dependent, but notice how it's going to cancel out with the mass in the basement, so this period should be independent of the mass of your object. D you can measure, that's just the distance between the pivot point and the center of mass, and you'll use a uniform object, so the center of mass will be at the center of the object. And then you'll be able to predict a period. Once you predict a period, you can hang it up and measure it and see if they agree. So that's what you guys are going to do. I hope it's fun, and I hope you get good results. See you soon. Bye.